All right, welcome to Tolleson Physics. So today what we're going to do is we're going to look at what happens with a pendulum, and more specifically, we're going to see what affects the time that it takes for a pendulum to go back and forth. In other words, its period. And so let's take a look at how to figure that out. So we're going to determine the period in a very similar way that we did for a spring. And as you notice, I've drawn a pendulum on there. We'll use that in just a moment. And so we're going to look at, okay, what's the restoring force in this case? Well, it's the gravitational force, but it's not all the gravitational force. So it depends on what angle, and that's what this force diagram is for here, is at some given angle, and the only force we care about is the one that's going to return it to its starting position. So the one that's perpendicular to its string, basically. And so when you look at theta being up here, translate it down to your force diagram, it turns out the gravitational force that we're interested in is mg times sine of theta. So that's our restoring force. So maybe I shouldn't have wrote it as Fg. That's the restoring force. And then we're going to use that as our net force in Newton's second law. So that really should say Fg perpendicular. And so when we combine that, we get MA equals mg sine theta. Now here's a nice little trick. When we do small angles, and this is actually important for you to understand, we're going to use a small angle approximation to get to where we want to go. And so the sine theta is approximately equal to theta in radians. And so we're going to use that. So when you're dealing with pendulums, you really can't go too much past 15 degrees or so, because then the small angle approximation starts to break down. So why am I doing that? Well, it gets rid of a trig function. So if I do that, then I get MA equals mg times theta, and that's in radians. So if I simplify that, mass cancels. Mass doesn't matter. And I get the acceleration equals the acceleration due to gravity times theta in radians. Okay, well, I don't want theta, and so we have this other diagram down here of a circle that just got covered up. But recall that for an arc of a circle, that arc length, which usually is s, but I wrote it as x, equals r times theta. So let's substitute that in. So theta equals x over r. So I substitute that in and I get the acceleration equals gx over r. And now we're dealing with a pendulum, and usually the pendulum, it's not listed as r, the radius of a circle, it's listed as the length of the pendulum. So I'm going to switch that variable to L. Okay, now we go back to what we had done before. We know what the position is based upon time. We know what the acceleration is based upon time. So once again, we're going to substitute those into that equation, and we get something that looks like this. And then what we can do is we can cancel out functions that are same on both sides, and we get omega squared equals g over L, something similar to what we got with a spring. And then we're going to do the same trick that we did before, where omega equals 2 pi over the period. I'm going to substitute that in, so I got 2 pi over the period squared equals gl. And I'm going to solve for t. And so when I solve for t, I get 2 pi equals the square root of L over g. No mess. All right, let's ask ourselves the same question. Does this make sense? All right, so the length increases, the period increases according to this. Does that make sense? And the answer is yeah. I mean, longer string, longer arc length, it's gonna take longer to get all the way across and back. What about the gravitational field? So if I increase the gravitational field, should the period decrease, right? It gets faster. Well, yeah, if I increase the gravitational field, that means there's a greater force on the pendulum. And so that greater force means greater acceleration, which means the period will be shortened. All right. And so interesting fact about this is the period is dependent upon the gravitational field, but not the mass. It's not the mass. So you can use a pendulum to figure out the acceleration due to gravity on any planet. Doesn't matter what mass you use. All that matters is the length. Then measure the period. You can figure out little g. All right, so now try this. Consider that you got a block of mass M attached to a string of length L, and it has a certain period. How will each of these affect the period of that block? So decreasing the length to L over 2, decreasing the mass to M over 2, or decreasing the gravitational field to G over 4. All right, so hit pause now and unpause when you're ready to reveal the answers. All right, so when you decrease the length, you're going to decrease the period by a factor of the square root of 2. Mass has no effect. Remember, mass has no effect on this, so there's no change. And then if you make the gravitational field smaller, well, that's going to make the period longer. And because of that square root, it's twice as large when the gravitational field is 4 times smaller. Okay, so there is your quick tutorial on simple harmonic motion for pendulums in this particular case. And really, these equations give us something about how is the period related to various parameters, and some parameters are missing that you would have thought would have been there. But also, don't forget about the forces and the conservation of energy that's going on in any of these systems.